And so far, in all of our Lagrange multipliers questions that we've considered, we've had exactly one constraint. So, question that we might think about, well, what if we have more than one constraint? And so as it turns out, we can handle this. And the answer to this is going to be, we have multiple constraints. Those turn into multiple Lagrange multipliers. So let me just write down a fake problem here. Suppose you want to maximize or minimize some function s subject to the constraint that g is equal to 0, but also subject to the constraint that h is equal to 0. Okay, well, what do we have then? Our corresponding Lagrange equation would be the gradient of f is equal to lambda times the gradient of g. If we would just stop here, this would make sense. But then plus mu, another Lagrange multiplier. So mu is going to play a parallel row to lambda here, mu times the gradient of h. Okay, so this is something we can do. Let's work out a problem where we apply this. So find the point on the intersection on the sphere, x squared plus y squared plus z squared is equal to 1, with the plane x plus 1/2 y plus 1/3 z is equal to 0. So find the point with the greatest x coordinate. So we can see here, this is giving us g. G is x squared plus y squared plus z squared is equal to 1. If you want to move that 1 to the other side so your constraint equals 0, that's fine. The plane equation h will be x plus 1/2 y and plus 1/3 z. Right now, we might not see an explicitly written out function to optimize, but greatest x coordinate tells us we're trying to maximize at x. So what are we going to do? Our function here. So we're going to maximize x. So this is our f, subject to g is equal to 1 and h is equal to 0, where g is x squared plus y squared plus z squared, h is x plus 1/2 y plus 1/3 z. Okay, so let's write down our Lagrange equation. So the gradient of f is going to be, well, the partial derivative of x with respect to x is 1. And the partial derivatives with respect to y and z are just going to be 0. And then the gradient g is going to be, so the x derivative here is 2x, the y derivative here is 2y, the z derivative here is 2z. The gradient of h is going to be, the partial derivative with respect to x is 1, then 1/2, then 1/3. So putting all of this information together, we have 1, 0, 0. The gradient of f is equal to lambda times the gradient of g, 2x, 2y, 2z, plus mu times the gradient of h, 1, 1/2, 1/3. Okay, so we have this equation. Let's write it out piece by piece, component by component. 1 is equal to 2x lambda plus mu. 0 is equal to 2y lambda plus 1/2 mu. And 0 is equal to 2z lambda plus 1/3 mu. So we need to solve. There's actually going to be 5 equations and 5 variables. Sounds a little daunting, but we'll be able to do this. 5 equations, 5 variables. Here, so the 5 variables are x, y, z, lambda, and mu. And the 5 equations, 1, 2, 3, and then the 2 constraint equations. Okay, so let's take a look at these two equations here. So I'm going to move the mu's to the left side of these equations. So we end up with negative 1/2 mu is equal to 2y lambda, or mu is equal to negative 4y lambda. And then similarly, this one would give us negative 1/3 mu is equal to 2z lambda. So mu is equal to negative 6z lambda. Okay, so we've got this and we've got this. Combining these together, mu is equal to this, mu is equal to this. This shows us that negative 4y lambda is equal to negative 6z lambda. Now, it would be nice for us to be able to divide both sides by lambda. If we divide both sides by lambda, then we'd have, negative 4y is equal to negative 6z. That would be good. We can only divide by lambda if lambda is not equal to 0. So, as it turns out, we can show that lambda is not equal to 0. Let me kind of get a contradiction here. Suppose that lambda is equal to 0. If lambda is equal to 0, this term here is 0, this term here is 0, this term here is 0. These all go away, and we end up with 1 is equal to mu, and 0 is equal to 1/2 mu, and 0 is equal to 1/3 mu. And so these would give mu has to equal 0, which contradiction. You can't have mu both equal to 1 and equal to 0 at the same time, so lambda can't equal 0. So, because lambda can't equal 0, we can divide both sides of this equation by lambda. In fact, I can divide both sides by negative lambda. So we end up with 4y is equal to 6z, which then solving this for y in terms of z gives us y is equal to 3/2 z. Okay, so let's just take a moment here. This is going to be a longish problem. So where are we? We're trying to use the Lagrange multiplier to solve this. There's two equations here, two constraints. Gray's x-coordinate gave us the objective function, the thing we're trying to maximize here. And so we are now trying to solve these 5 equations with 5 variables, and we're making progress. We got y has to equal 3/2 z. And in fact, this much, we're at a point where we can stop working with the Lagrange multipliers lambda and mu between y is equal to 3/2 z and the two constraint equations, x squared plus y squared plus z squared is equal to 1, and x plus 1/2 y plus 1/3 z is equal to 0. We can solve for x, y, and z from here. Okay, so what we're going to do is let's take this new relation and plop it in over here. So replace y with 3/2 z. So that would give us x plus 1/3 z plus, I should be more careful here, 3/2 times 1/2 z plus 1/3 z is equal to 0. And so this is 3/4 z plus 1/3 z. That ends up as 13/12. Z is equal to 0. So x is equal to negative 13/12 z. So what we've accomplished here is that we've written, so we wrote y in terms of z. Here we just wrote x in terms of z. And so now we're going to plug in for both of those here. X squared, what is x? X is negative 13 over 12z squared, plus y squared, what is y in terms of z? Negative 3/2 z squared, plus z squared is equal to 1. And so putting all of this together, there's a lot of arithmetic, a lot of algebra simplification to do here. You get 637 over 144 z squared is equal to 1, which gives you two solutions. Z is either plus or minus 12 over 7 square root 13. So we have two critical points. One corresponding to z is positive 12 over 7 times square root 13. The other is where z is negative. So one critical point is when z is 12 over 7 times square root 13. The other is when z is negative 12 over 7 times square root 13. And then we can use these two relationships here to figure out x and y. So if z is 12 over 7 times square root 3 and y is 3/2 times this, then we end up with 18 over 7 square root 13. And if x is negative 13 over 12 times z, then we have negative 13 over 7. We can also do this by plugging in the other one. If z is negative 12 over 7 times square root 13, y here 3/2 times this will be negative 18 over 7 times square root 13, and x will be negative 13 over 12 times this, which will be, I forgot to put a square root here. I'm copying off of some notes there, and that looks a lot better. Okay, so at the end of the day, here are our two critical points. If you graph things out, let me just show a picture here. Taking a look at the picture here, we can see this is going to be a closed bound domain, so we're guaranteed to have a min and a max here. And accordingly then, we have to pick the one with the largest x coordinate. Which one has the largest x coordinate? This right here. So this is the point on the intersection of the sphere x squared plus y squared plus z squared is equal to 1, and the plane x plus 1/2 y plus 1/3 z is equal to 0, with the largest x coordinate, which is square root 13 over 7. Okay, so longish problem, I guess, what are the morals of the stories here? So we had to write down, we have two constraints, we have two gradients, and we have two Lagrange multipliers in our Lagrange equations. And then it just becomes a big crunch out to solve a system of equations. You can see the thing that we tried to do was that we tried to get rid of mu and lambda as fast as possible. We were aided by realizing that lambda could not be 0 here. And as soon as we got it down to, so y is 3/2 z, we got it down to 3 equations in the original variables x, y, and z. We're trying to get rid of the Lagrange variables, the Lagrange multipliers, as quick as possible. We have y written in terms of z. We managed to get x written in terms of z. We substitute it into this equation so that at the end of the day, we only have one equation in one variable. We were able to solve that equation to get z is plus or minus 12 over 7 times square root 13. And then we go back and we're able to obtain x and y in those two cases. Okay.